evaluation theorem. Integral a to b, that you can do capital F of b minus capital F of a. All right. Test is on
Tuesday?
Thursday.
right? Today's Tuesday. So our test is on Thursday. Would you like for me to talk about the test first?
Yes.
Yes, and then we can talk about, we're going to do a little bit of 8-2 today.
I'm going to need 18 for the test.
Yes, but not necessarily what I'm going to do today. I'm going to stop it at geometric series. Okay, that's where the test will stop. So,
It's so hard.
here it is. So I'm going to show you the test. You can't say I didn't show you the test. See, I showed you the test before. We have
I'm going to zoom in the video.
11 problems. Yeah, I'm in high def. That might come back to it. There are 11 problems on this test. You ready? I'm going to tell you kind of what you need to look at. You need to be able to find the area bounded by some curves. And take it all the way. That means integrate it, give me a numerical answer. Which means you're going to have to be able to sketch something, right? I'm going to expect that you can draw the regions, label everything nice. You need to be able to set up an integral, set up but not evaluate an integral that represents the volume of a solid when it's rotated around the x-axis, the y-axis, and various lines. So what I mean by that is you need to be comfortable getting a region between two curves. You need to be able to come up with formulas that would represent that region wrapped around the x-axis, around the y-axis, around
2?
pardon?
Around
Around
2?
2.
X equals 2. Y.
Okay, yes. So like around possibly an axis over here on this side of it, or some rotational axis over here, or perhaps above it, or perhaps below it, and of course the x and the y axis. So coming up with formulas for all those different variations, yes.
So you're going to ask this question and you're going to give us like maybe like 3 little bullet points, get the formula for this, and this, or no?
No, I'm going to have them as separate problems. Okay? I'm going to have them as separate problems. But what I will do to cut down on time is I'm going to keep it the same region for all the different rotations. So that way you have to come up with that region, right? That first time, you've got to get that right. Because if you don't get that region right, every problem is going to be wrong.
No pressure.
Okay? But it's better than you having to come up with 5 different regions, 5 different times, because that would take you a lot more time.
I'll
Yes.
see about that after the test.
We will. We will. The region is fair. Okay? What I'm going to use is a fair region. I'm not going crazy here. All right?
Thank you.
Okay. Next thing. I'll just read you this here. The base of a solid region is bounded by 2 curves. I'm not telling you what they are.
Say that again?
The base of a solid region. The base of a solid is the region bounded by 2 curves. Cross sections of this solid perpendicular to the x-axis form something. Squares maybe, equilateral triangles, semicircles, circles.
Is this the one we did at like the end of class?
Yeah, at the end of class we cut it, right? Now, I believe I have a video for homework solutions that has me doing, yes? Y'all see?
Yeah, I'm pretty sure.
Pretty sure I've done, you've got to be able to do one of those. Now, at the end of class today, I will open up for questions, and if someone says, hey, can you give us something like that one with the cross sections, I'll start working one out, all right? But does everyone understand what I'm referring to here?
Right.
Okay. You need to be able to do one of those. You need to be able to set up an integral but not evaluate an integral for either arc length or surface area. I'm not going to tell you which one. And the main thing on that one is I want you to be able to do any weird sort of algebra when you're trying to clean up the integral. So you need, there's one I did in class where the algebra was weird and things started to cancel and we got perfect square trinomial, and you need to be able to do that for arc length or possibly surface area. But you don't have to evaluate it, okay? You need to be able to do an improper integral. Now that's section 6.6. So that was one of those integrals where you have a discontinuity, that your function is undefined somewhere on the interval of integration. So one of those, and that one I will ask you to take the whole way. In fact, the instructions say, determine if this is convergent or divergent. If convergent, then evaluate it. If it's divergent, you just have to state it's divergent. Well, it's going to be something. Okay. And then, okay, now we're moving to chapter 8. Okay. You need to be able to find the formula for a sequence. So if I list out the sequence, you know, the braces and then the numbers, right? This number, comma, this number, comma, this number. You find the pattern, you come up with the formula. You need to be able to do that. Okay? And I might give you multiple sequences. And you know, part A, B, C, and you have to find formulas for each one.
Choose one.
Number 9, do these sequences converge or diverge? So that's still 8.1. I give you a sequence, and you find out if it converges or diverges. So that's where you let n go to infinity, and you could get all sorts of things happening there. You might have to bring in L'Hopital's rule, whatever. And I did send out an email.
Yeah.
I did send out finally the email for L'Hopital's rule. Yeah, okay, just so you know it's there. It's actually, I covered L'Hopital's rule in Cal 1 over a period of three classes. It was at the end of one class. It's about 30 minutes of one class. So that's the first video should pick up right where I start L'Hopital. You click on the link. And then the next class, the whole class is L'Hopital. And then the following class is the first 10 minutes. I do one problem. I think I did that problem in this class. It was the one for E. Okay, it's limit x goes to infinity 1 plus 1 over x.
Is there any related examples like for their homework in a sense, or
Is there what?
like are there related examples for like if you want to go back and try to attempt it to really get proficient?
What, the homework out of that section?
Is the video going to say like it as far as where this is the homework section?
It might. I don't recall. I think for that class they have a pre-printed.
Yeah, we did last year. We had a
Yeah, so yeah, if you're interested in the homework on that, you can just
Go in the files and see. Well, no.
you can email me.
Okay.
I might have it laying around. Okay, the last two are geometric series.
No.
So harmonic is not even.
I won't do harmonic. I mean, it's yeah.
Don't you start?
So yes.
Should we be looking at both type 1 and type 2 proper integrals?
No, just the type 2. Just type 2, because on the last test we did type 1. Type 1 is like where your limits of integration are infinite. So like go to 0 to infinity, that won't be on this test. All right, I think that's more than fair to tell you what's basically on that test. Let's talk about geometric series briefly. There's a couple of different ways that I could give you a geometric series. Okay, I could give you well, let me first remind you what it was. A geometric series looks like this. But that we said was the same as starting at 0 and r to the n instead of, oh, you know what? My microphone. I forgot to plug in this thing here. It's recording right now. It's just, it was the microphone on the camera as opposed to the microphone on me. So the audio is going to be a little, it'll sound like I'm in a toilet when you hear that first part. This will sound a lot better. Okay. So two equivalent formulas for geometric series, right? And we know that this will equal one of two things, right? It's either going to be a over 1 minus r, as long as the absolute value of r is less than 1. And it will diverge, right? If the absolute value of r is greater than or equal to 1. So when it comes to me asking you to evaluate a geometric series, I could give you a geometric series like this. So as an example, I could say, hey, what's the sum n equals, let's say, 1 to infinity of 4 to the n plus 1 over 7 to the n minus 2. Where I actually give you a summation, and you have to turn that into one of these, right? That's one way I could do it. Or I could give you something like this. 5 halves plus 5 fourths plus 5 eighths plus 5 16ths plus 5 32nds plus dot, 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 like that. Which means you would have to actually see the pattern, come up with the formula, right? Rewrite this in sigma notation, and then continue, right? So does anyone know, can anyone tell me what this n equals 1 to infinity of 5 over 2 to the n? Right, that would be it. And then you would have, so now from here you're back to like here. You have to get it to look like one of these, right? And since n is starting at 1, you'd want to make it look like this one, right? Understand? Another way I could do it is to give you something like 0.512. Yeah, 1, 2, 1, 2, repeated forever, right? Because we did one of these at the end of class last time, right? First, you write that out as, 5/10 plus 12 thousandths plus 12 millionths, and so on. And so you write it out. Then it looks like this, right? And then from there, you go to the formula. And then from there, you go back up to here. Got it? Those are like the 3 different ways you can see a geometric series that I would present it to you. So be prepared for any of those. If I give you one of these, then it kind of kills them all with one shot, huh? You got to be able to write it as a sum and then convert it to the summation formula and then convert it up to this. All right. Try and stop me somewhere, if I don't stop myself. Try and stop me 45 minutes till. So maybe around noon. Okay? And at noon, I'll talk about any questions you might have on the test. What are we about to do? We're still in 8.2. All right. So we talked last time about a harmonic series. We've talked about geometric. Those are the 2 types of series we've talked about. All harmonic series do what? Diverge, right? And the idea of a harmonic series is that you have, what's going on? K over n. Really, it's like any constant over a linear expression in n. Right? That's the idea of a harmonic. Geometric, the n is up in the exponent, right? You've got this number that keeps getting raised to this power. It gets bigger and bigger. All right, so we're going to talk about a couple of other series today, but there's a couple of theorems that we want to get through. So the first theorem says this. If you have a series, all right, I'm just going to write this. Now, I did not put what n starts at and n goes to infinity, all right? But I'm not going to put n equals 1 because it could be n equals 0. Doesn't matter. We're just going to assume that this is an infinite series. I'll put infinity up there. All right, so we have an infinite series, all right? If this series converges, then a sub n must go to 0. All right. Someone explain to me what that's saying?
If it converges to anything, it goes to 0.
What goes to 0?
A sub x.
What's a sub n?
The series?
Close, not the series. The series is adding up all these guys, right? If I add up all these guys, and that adds up to be a number, if it's getting closer to a number, this theorem says that means the sequence must converge. The sequence must converge to 0. All right? Understand this?
So any of them converge?
Hmm?
Any of the series converge?
Any series. If a series is convergent, I guarantee you the sequence converges to 0. Now we have to be extremely careful with this, all right? Extremely careful. This is where we talk about logic, okay, and we talk about proofs and things like that. I want you to look at this series right here. What type of series is this?
Harmonic?
It's harmonic, okay? It's harmonic. What does the sequence do? Well, what is the sequence? What is a sub n?
1.5.
No. Yeah, okay, yes, but in a formula sense, what is a sub n here?
1.
1 over n. That's the sequence, right? I'm adding up all those? That's the sequence. What does this sequence converge to? It goes to 0, right? You take the limit as n goes to infinity. This thing goes to 0, right? You all following me? This goes to 0. Does that mean this converges? No. Look at what the theorem says. The theorem says if the series converges, I promise you the sequence must go to 0. This theorem does not say that if the sequence goes to 0, that series must converge. You cannot use this backwards. All right? You can't. So does this series converge? No. This diverges. Why? Because it's harmonic, right? This diverges. So this diverges, and that goes to 0. What I'm, again, trying to show, this is the biggest mistake I see students make in the very beginning of series, is that they sit there and they go, okay, does this series converge? Does it converge? And they look at the inside and they go, oh shit, that goes to 0. Yes, it converges. No. You can't do that, all right? You can't do that. Now, let's talk, is this kind of clear? A little bit? Okay. So let's talk about this. Why would I give you this theorem then? Because in order to use the theorem, what do you have to know? If it converges, and that's pretty much what I'm going to ask you to start. Does it converge? Well, you don't know, right? You don't know necessarily. And so that theorem is not very useful to us. But when it comes to logic, the logic of things, I'm going to show you something called the contrapositive statement. So this gets into logic in how we prove things again. If I write this is the classic example I like to use. If you're in Cal 2 class, right here, sitting in this room, okay? If you're in this class right now, then you're at NBC. Do you agree? Okay, if you're sitting in this room right now, you're at Northwest Vista College. So you agree that this is an if statement. If this is true, then that has to be true. But it can't work the other way around. If you're at Northwest Vista College right now, are you sitting in this class? No, not necessarily. And that's exactly what this theorem is like. If this is true, then this is true, but we can't go backwards, right? But what can we do? What we can do is what's called the contrapositive. Now, you're not going to be tested on this, but what can I gather from this? What could I use? So watch this. Let me write this backwards. At MVC, if this, then this. But I'm going to negate both statements. Watch. If you're not at NVC, then you are not in this class right now. Is that true?
Yes.
That's true. And that's called the contrapositive. So what you do is you're allowed to take an if-then statement and reverse it if you negate both statements.
Is this the hyphenation of contradictive positive?
Contrapositive? Mm-hmm. Yeah. So with this in mind, these in our logic system, if you ever take a logic class and do truth tables, the truth tables for these two are identical. That means that you can take any if-then statement, reverse it, and negate both of the statements, and it's logically equivalent. So if I come back over here, what's the logical equivalent to this theorem? If the what doesn't converge? If the sequence does not go to 0, if it does not go to 0, see my little knot in there, little arrow, little cross through it? If the sequence does not go to 0, then the series does not converge, which means it diverges. And this right here, everyone, is called the nth term test for divergence. And maybe I should have started this all out by just explaining kind of where we're going. I don't think I did a good job of that. Look, I've given you two types of series, right? Geometric and a harmonic. And they're very easy to look at, relatively easy to look at, and be able to determine what's going to happen. If it's harmonic, it diverges, we're done, right? If it's geometric, we just have to figure out what R is, right? What we're trying to lead up to is, what if I hand you a series that's not geometric, that's not harmonic, and it's just some weird series, and ask you, does it converge? We need to start coming up with ways to figure that out. And this is the first thing that we use to try and figure out whether a general series converges or diverges. We use this thing called the nth term test for divergence. But it only tests for what? Divergence. It will never tell you whether or not something converges, ever. It will just tell you if it diverges. That's all. So whenever we look at a series, the first thing we will do, first thing, is run this test. Yes? No. Because this is good. Think about it. This test tells you what, the only thing it tells you is whether or not it diverges. So it's like, let me try and think of, trying to think of a good, okay, I think I have a decent analogy. No, hold on, that's not working. Okay, here, yes. How many different blood types are there?
5?
No.
I don't care, there's more than 2, right? Okay, there's more than 2? I have a test that you can take. Give me a little sample of your blood. It'll test whether or not you're O. Okay? If you're not O, it does not tell you what you are, right? It just tells you whether or not you're O. I still don't think this is working as a good analogy because there's only 2 options here, convergence and divergence. But, no. I'm trying to think of something that you could be possibly twice, or both conditions could hold. Let me think about it some more. It comes from this, though. Look, this test tells you whether or not you diverge, right? It'll tell you, yes, you diverge, right? But if the test fails, it's saying, I don't know if you diverge or converge. You could still diverge, but I don't know if you do.
So there's parameters that it lies outside of, even if you run the test, it might not fit the protocol.
That's right. Let me give you two examples of this, okay? The two examples I have are look at this right here. Look at those two series right there. Look at those two series. Run the nth term test on both of those. So what is the a sub n in this one? 1/2 to the n. I'd like for you to take the limit as n goes to infinity of that. It should go to 0. Because 1/2 squared gets smaller, 1/2 cubed gets smaller, that goes to 0. Everyone agree? Okay. What about this one? Limit n goes to infinity. What happens here? You get this, right? Goes to 0. Let me give you one more. Limit n goes to infinity of n, which goes to infinity, right? Okay, so let's just take a look at these three series. Running the nth term test, it says that if this thing does not go to 0, then the series diverges, right? That's what the test says? So when I run the test on this one, what do I conclude? Okay, a sub n goes to 0. What's my conclusion?
It does not diverge.
It does not diverge. Inconclusive. Look, the test told me nothing. Because what do you need for the test to work? You need this to not go to 0 for the test to work, right? This goes to 0. If it goes to 0, the test doesn't work. So maybe we can go back and we can think of, I'm trying to think of a freaking analogy that would work for this. Okay, so I need to come up with a good analogy. I'm trying to stick to something. Okay, let's go with something that would have two choices. So how about I'm testing, I have a test that checks whether or not you're male, okay? Somehow looking at your chromosomes or something, right?
Be careful.
Okay, yeah. Okay, male or female, right? I've got this test. But in order to run the test, right, I have a condition that must be met, okay? So I need to be able to see you, okay, before I run the test. If I can't see you, it can't be a conclusive test. Basically, you throw it out. I don't know what the result is. I don't know if that makes any sense, but there is a condition that must be met before. If that condition is not met, then my test doesn't work at all. The test only works under this condition. I hope that helps. Okay. So look, and this shows you two examples. This is a geometric series that converges. This is a harmonic that diverges. They both have the same thing happening, right? The sequences both go to 0. This test couldn't possibly have told me anything then, right? So anyway, okay, so I hope that makes some better sense. Look at this one. Does that go to 0?
No.
No, that diverges for sure, because then I can apply the test. All right, so nth term test is the first test that we run. If it goes to anything other than 0, you're done. All right.
So if it goes to a number then it goes to infinity?
No.
So it's
Well, if what goes to a number, what goes to infinity?
Like how?
Like if you run the test and it gives you 2 or 6 or 12 or infinity.
Then the series diverges.
Not the sequence.
But if it at all goes to 0, then
You don't know
then
anything.
You just basically throw it out the door.
You throw it out. Yep. Okay, so look at this one right here.
I don't know. You just put
Look, here's the reason why we like the test. The reason why we like this test, because you may be like, well, what the hell's the use of the test, right? Because if it works out for us that the limit is not 0, you're done. And trust me, once you see all the tests that we're going to have to learn, you're going to want to run this first, because you do not want to spend 30 minutes trying to run a test that you never should have run to begin with, because it diverged right off the bat. So this is not a very it's powerful. It's not very useful because it doesn't come into play a lot, but it's something that's there. And it's easy to run the test, right? So look at this. Does this converge or diverge, or do you not know? So what happens? I'm going to put here, does this converge or diverge, or you have no idea? You don't know. So we're going to run the nth term test, right? So I'm going to take the sequence, right? The sequence a sub n is 2n plus 1 over n plus 4. And I'm going to run the limit on that, right? What's the limit as n goes to infinity of this? You get infinity over infinity. You can do L'Hopital because you could turn those into functions of x. Everything would work out. What would your limit be? 2. 2 is not 0. So this series diverges. This diverges by the nth term, and you need to write that out too, test. I did L'Hopital in the background.
Did you have to in order to do that?
No, I could have done something else. Divide top and bottom by n. Is that what you're saying?
No, the way you wrote it, is it by the?
By the nth term test. Nth term test. Now, in fact, later on, once we get more tests, and I'm going to give you a sheet at some point here that's going to have all the tests. I'll give that to you next time we meet, which will be next week, right? Thursday will be the test, and next Tuesday I'll give you the sheet. So what you'll do as time goes on here is you'll actually write out, first thing I'm going to try, nth term. Okay, you'll write nth term, and then you'll show the work. And if it finishes, you're done. But if this comes out and this turned out to be 0, what would I say? Fails, and then you go to your next test, whatever that test is, and you have to choose which test fits for this problem. So it's going to be like, okay, one thing followed by the other, and hopefully at some point one of the tests will work.
Is there a certain order, like best way to do the test, or?
After you do enough, you get kind of a little bit of experience with it. You'll be recognizing patterns in the actual series itself.